Hey, welcome back. I had this done early. Actually, there's the camera. I had this done early, but I had to take a break for physical therapy, and I'm killing it. So I'm really looking forward to being back in class next week. We'll have 3 days of review. You guys will be set. Let's talk about chapter 8. Yes, I did ask Carla to lecture section 8.1 today, but it's been a while since I've seen you, or you've seen any math instructor necessarily. So I don't know how many questions you had. I don't know how far she got into the lecture. So I thought I'd just send you the whole lecture anyway. This way, if you went to class, you get two perspectives instead of just mine. All right, so chapter 8 is all about matrices. Matrice is the plural of the word matrix, and it has nothing to do with Neo or the blue pill or the red pill. All right, in 8.1, we're going to look at systems of equations with matrices. In this section, we will study a streamlined technique for solving systems of linear equations. This technique involves using a rectangular array of real numbers called a matrix. Plural of matrix is matrices. The entry in the ith row and jth column is denoted by the double script notation Aij. So it's row I, column J, always row then column. So A23 refers to the entry in the second row, third column. A matrix having m rows and n columns is said to be of order m times n. If the order happens to be like a 2 by 2 or 3 by 3, or if m and n are equal, then we call it a square matrix, and we'll usually use n by n. I've very rarely seen it m by m. For square matrix, the entries A11, A22, A33 right here, we call that the diagonal. My dogs are pretty vocal today. I don't know, something's going on in the neighborhood. So I apologize for the background noise. So if m and n are positive integers, and m by n, right, m by n matrix is a rectangular array, and this just has numbers in it. Each entry is a number. There are m rows and there are n columns. All right, so remember, m rows, n columns. Here we go. This matrix, I want something different. I'm going to point with yellow. Okay, this matrix has one entry. There is one row. There also happens to be one column. That makes this a size 1 by 1. This is not the absolute value of x. This is 1 by 1. I've got to go tend the dogs real quick. I'll be right back. And we're back, and I have no idea where I left off because, I do that in class too. So let's look at this second matrix. There are two rows that go across, so two rows. 1, 2, 3 columns. So this is a 2 by 3 matrix, all right? 2 by 3. In C, there are two rows, so R is 2. I got tired of writing rows and columns. It's a little bit of laziness, but I'm going to go with it. There are two columns, row 2, columns are 2, so it's a 2 by 2 matrix. This is a square matrix. And yeah, 4 items makes a square. There are 1, 2, 3 rows, only one column. 3 rows in one column will be a 3 by 1 matrix. All right, so all we're doing is counting rows and then columns. This is the first place really where the alphabet doesn't help us. All right, here we're going against alphabetical order. It's rows and then columns, the fewest number of letters. I don't know how you want to remember it, but rows then columns, rows then columns. Okay, now let's look at a couple of these definitions here. A row matrix is a matrix that only has one row. A column matrix is a matrix that has only one column. So this is a column matrix. This is a row matrix, I guess, but only by default. Column matrix, a row matrix would look like this, only horizontally instead. We also have an augmented matrix. An augmented matrix of a system of equations is a matrix derived from a system of linear equations, each written in standard form with a constant term on the right. Remember, we always lined up x's, we lined up y's, we line up z's, we line up equal signs, and we have our constants. As long as we're keeping them in this ordered system, this is kind of a rectangle that we're dealing with anyway. Well, we can take this system and using dotted lines for our equal signs, we could write just the coefficients in order. First column x, second column y, third column z, fourth column is going to be our constants. I'll trigger finger there. So we have 1, -4, 3, and 5. 1, -4, 3, and 5. My first equation becomes my first row. And since I'm keeping everything organized, my first column is x, my second column is y, my third column is z, and then I have the answers. So we'll have -1x plus 3y minus 1z equals -3. 2x's 0y's minus 4z equals 6. And this is the augmented matrix. It gives you the entire system. What we could do, though, is ignore the answers, the right-hand side of the constant values, the right-hand side of the equations. And this is the coefficient matrix. The coefficient matrix is just the coefficients of the variables in your system of equations. And we're going to use this and manipulate it in several different ways as we go forward. Okay, so this is going to be very repetitive. For elementary row operations, we can interchange two equations. We can now interchange any two rows. We can multiply an equation by a non-zero constant. We can multiply a row by a non-zero constant. You may have noticed in chapter 7, I even called them row 1 and row 2 because I forgot to call them equations in that chapter. We could add a multiple of a row to another row. Right? The same operations we had before for making a coefficient of 1x and then eliminating x's below, and then make a coefficient of 1y, eliminate y's below. Same process, only now we don't have to write the x, y, z. Okay, a matrix in row echelon form has the following properties. 1, any row consisting entirely of zeros occurs at the bottom of the matrix. For each row that does not consist entirely of zeros, the first non-zero entry is a 1. All right, we're always making ones. The coefficient of x in your first equation should be a 1. The coefficient of y in your second equation should be a 1. It's the same leading ones that we're using now. For two successive non-zero rows, the leading one in the higher row is farther to the left than the leading one in the next row. So if I have a leading one here in the first column, then it has to be in the first row because further to the left is higher in the matrix. A matrix in row echelon form is in reduced row echelon form if every column that has a leading one has zeros in every position above and below it. So in echelon form, we will have something like this. If you want it in reduced row echelon form, then you have to get zeros above as well. Now, the call for that is not very important. I'm going to call it ABC. I'm going to call it whatever junk that was that I just scribbled with the mouse. Right, reduced row echelon form, we need zeros above as well. And this particular matrix, this coefficient matrix, has a form that we'll talk about in a minute. So Gaussian elimination with back substitution. First, we'll write the augmented matrix of the system of linear equations. Then we'll use elementary row operations to rewrite the augmented matrix in row echelon form. And then we'll use back substitution to find the solution. This is exactly like we did in 7.3. If we wanted to Gauss-Jordan, so Gaussian elimination, Carl Friedrich Gauss looks like the royal ugly dudes from Bill and Ted's Excellent Adventure. Jordan came along about 50 years later and added to this elimination. So I think Jordan was he was early 1900s, maybe late 1800s. That's when you have the zeros above as well. All right, I only care about us getting leading ones and zeros below. Gauss-Jordan has leading ones, zeros below and above. Let's look at some examples. All right, and this is This is some serious, like, it's going to take a minute, all right? This is where we use a little bit of paper. X plus y plus z equals 6. 2x minus y plus z equals 3. And 3x minus z equals 0. The first thing I'm going to do, since we're all lined up, x, y, z equals signs constants, I'm going to put this in matrix form. So I look at the coefficients. 1, 1, 1, constant of 6. Coefficients 2, negative 1, 1, constant is 3. Coefficients are 3, 0 y's, negative 1 for the z, and a constant of 0. Now I want to get a 1 up here. It's already there. I'm good to go. I want to make zeros below it. I'll always use this leading 1 to eliminate and get zeros below. So I'll multiply negative 2 times row 1 and add it to row 2. So that's exactly what I did. Multiply everything in row 1 by negative 2. Add to row 2, and I'll get a new row 2, which is 0, negative 3, negative 1, negative 9. So I think this is the same example as in 7.3. And I think this is one where I had to take a nap before I found the answer. Would you believe I messed this one up again? But it's right now. I fixed it. Right here, I called that a negative 3. There's no negative sign there, and I inherently put one. Also, we want to make a 0 here, so I'll multiply negative 3 times row 1, add it to row 3. 0, negative 3, negative 4, negative 18. Our new matrix using our row 1, and our new row 2 and new row 3. Next step, I want to make this a 1. If I want to make that a 1, I'm going to divide it by a negative 3. That's going to be my new row 2, and I've put it over here. I keep row 1, 1, 1, 1, 6. New row 2 is 0 divided by negative 3. Negative 3 divided by negative 3. Negative 1 divided by negative 3. And negative 9 divided by negative 3. That's the only thing I changed. I only changed row 2 to get this matrix. But remember, each time with this process, I no longer need to look at this original. Now I no longer need to look at this matrix. This is the one I'm solving, and the solution of this will solve each of the matrices up the way as well. Now that I have a leading 1, I want to make a 0 below it. To make a 0 below it, I'll multiply row 2 by 3 and add it to row 3. So I multiply each term by 3. Write in row 3 as it stands. 0, 0, negative 3, negative 9. And this is going to be my new row 3. And I notice that if I divide both terms by a negative 3, it'll simplify it for me. So I made a 1 on my way to writing the new matrix. So I did kind of step 5.5 right here. Okay, so I have leading 1s. I have zeros below them. This is Gaussian elimination. This says z equals 3. This says y plus 1/3 z equals 3. So if z is 3, 1/3 of 3 is 1. Y must be 2. And the top equation, top row, says x plus y plus z equals 6. We know what each column stands for. So we put in the 3 for z, the 2 for y, and x must be 1. Excellent. Always check in the original problem. There's the system. Make sure it works, or check your 7.3 notes. Next problem. We're going to solve again. X minus 2y plus 3z equals 9. That equation turns into the row 1, negative 2, 3, 9. Similarly, my next row will be negative 1, 3, 0 z's, and a minus 4. Third row, 2 minus 5 plus 5, 17. I have a 1 here. That's fantastic. Now I need to make zeros below it. To make a 0 in row 2, I can just add these two together, so row 1 plus row 2. And to eliminate this 2, I can multiply row 1 by a negative 2. Add straight down, as we do, and we have our new matrix, a leading 1 in the upper left-hand corner, and zeros below it, and I just so happen to already have a leading 1 here. Fantastic. And I just need to eliminate this, turn this into a 0. But look, 1 and minus 1, I can just add these two. And I end up with 0, 0, 2, 4. It's a new row 3. And just like I did on the previous one, I see that if I divide divide every term by 2, take half of every term, I'll have a leading 1 here as well and take care of that little step at the same time. Now I know that z equals 2. Y plus 3z equals 5. If z is 2, that's y plus 6 equals 5, so y equals negative 1. And x minus 2y plus 3z equals 9. We know z is 3. Y is negative 1. This will be x plus 8 equals 9, so x equals 1. Always check again in the original system. Make sure it is indeed a solution. With math, you know the answer is right before you move on. The hardest part, typing it into WebAssign. All right, next problem. X minus 3y plus z equals 1. 2x minus y minus 2z equals 2. And equation turns into row 1, 2, minus 3, negative 1. I have a 1 in my upper left-hand corner. I need to make zeros below it. This is the exact same process as 7.3, only we don't have to keep writing x, y, and z. For a lot of mathematicians, myself included, we're lazy and we get sloppy, and those x's start looking like y's and those z's start looking like 2's, and you get kind of mixed up. So the matrix takes the letters back out of math, so you're only dealing with numbers. And we could generally handle numbers, right? All right, so we need to make zeros below it. I'm going to multiply negative 2 times row 1, add it to row 2. And I'll multiply negative 1 times row 1 to add it to row 3. I multiply through appropriately, add row 2, and I have 0, 5, negative 4, 0. A new row 3 is 0, 5, negative 4, negative 2. Now something looks funky here. And once I see that these are exactly the same except for in this last part, I ask myself, did I mess up? And so I go back and I check when I'm at this stage, and in fact I did not mess up. Okay, so we'll come back to this. Maybe it works out. I need to now make a 1. So I'm going to multiply 1/5 times row 2 to get my new row 2. That's 0, that's a 1. Negative 4 divided by 5, right? Negative 4/5, and 0 divided by 5 is 0. I need to make ones, I have a 1, so I need to make a 0 below it. I'm going to multiply row 2 by a negative 5. When I multiply, 0 times negative 5 is 0. 1 times negative 5 is negative 5. That's what we needed. Negative 5 times negative 4/5. The 5's cancel. Two negatives make a positive, so I get positive 4. And negative 5 times 0 is 0. And when I add straight down, wouldn't you know it, I have a row of zeros, but it's not all 0. This says that no z's, no x's, no y's, but we have negative 2. If we have nothing, how can it be negative 2? Well, that's because there's no solution. So if you get a nonsense equation like this, just like we did in section 7.3, the answer will be no solution. All right, one more. Here we go. Solve the given system. First, we write it as an augmented matrix. I've noticed that a lot of times I forget to write my dotted line here, the augmented little symbols. Use it or not, it's not going to change your numbers at all. It does make it kind of look nice if you're not sloppy with it. And you'll find textbooks a lot of time drop that notation in between as well. Mathematicians, as very particular as we are, we're also very sloppy in other ways. I apologize. So we want to make a leading 1, and then we want to make zeros below it. I'll multiply negative 2 times row 1 and add it to row 2. I'll multiply negative 3 times row 1 and add it to row 3. But that row 1 doesn't change, right? I've used it, and then I keep it the same always. My new row 2 is 0, negative 3, 15, 21. My new row 3, when I do the operations, is 0, 3, negative 15, negative 21. And again, look at that. Zeros, 3s, 15, 21. My signs are weird. Something crazy's going on. But let's see what happens. Let's make this a 1. So I'm going to divide by negative 3 or multiply by a negative 1/3. Divide each thing in row 2 by a negative 3. That'll be 0, 1, negative 5, negative 7. Now that I have a 1, I want to make zeros below it. If I make zeros below it, multiply negative 3 times row 2, add it to row 3. When I add straight down, oh look, those signs being different, yeah, they're going to cancel everything out. And we know that if you have a row of all zeros, that makes sense. 0 equals 0 is always true. So this is when we let z equal z. It's the third equation, so we choose the third variable. Let z equal z, and then we can solve for y. Y minus 5z equals negative 7. Add 5z to both sides. And then we can use the solutions for y and z to solve for x. Exactly the same problems that we had in 7.3. Slightly different approach, but you can see at every step along the way that it's exactly the same thing. All right, that's it for 8.1. Full lecture. No worries if you didn't make it to class, but thank you so much if you did manage to get there and ask some questions.